Most of you know that carbon is essential for life. Why? Well, a remarkable number of many different types of molecules are necessary for us to exist. Not only do we need this tremendous diversity of molecules with widely varying properties, but these molecules must also be able to form and react and break apart and reform and interact with each other in very specific and highly coordinated ways. The only element that is able to do this is carbon. Only carbon is able to make the necessary structures for life. Only the structures made from carbon are able to interact in the very specific and necessary ways. There are 5 reasons why this is the case. Number 1, carbon forms stable bonds with itself. The only element that can make stable chains of atoms is carbon. The unique stability of carbon-carbon bonds allows an almost unlimited number of organic molecules of almost any size. Number 2, carbon can form up to 4 bonds. Nitrogen can give you 3 bonds, oxygen 2. Silicon can also form 4 bonds, but there are other reasons why it doesn't work as the basis for life. So this ability to form multiple bonds is crucial to make the molecules needed for life. One example is lipids. Every cell membrane, even the cell membrane of the simplest life form, is made up of many different types of lipids. To give the cell membranes the properties that they need, there must be a mixture of lipids of varying lengths and lipids with differing numbers of double bonds and triple bonds. Because carbon can make 2, 3, or 4 bonds, carbon has the ability to make all the varying type of lipids needed for life. Number 3, the third reason why carbon is the only atom that can be used as the basis for life, is that carbon not only forms multiple bonds with itself, but also with other atoms. Now, silicon can also form 4 bonds, but silicon has a difficult time forming multiple bonds with the other atoms necessary for life. For example, silicon can't form a double bond with oxygen. And you know that one of the molecules we need for life is carbon dioxide. Well, that's carbon forming double bonds to oxygen. Well, silicon can't do that. Fourth reason why carbon is the only atom that can be used as the basis for life is that the energy levels of the carbon-carbon bonds are just right for the type of biochemical manipulation that we need for life. Remember, the molecules needed for life must also be able to form, reform, react, break apart, interact with each other in very specific and highly coordinated ways. So these bonds have to be strong enough for the molecules to last and do their job in our bodies, but at the same time weak enough to allow enzymes to come in and break those bonds during the reactions necessary for life. So carbon bonds are what is called metastable. If the bonds were stronger, like with the bonds between nonmetals, then the reactions needed for life couldn't happen. If the bonds were weaker, then the molecules wouldn't last long enough to do their job. So this metastable property of carbon bonds is crucial for life to exist. And it just so happens that that property is most efficient at the exact same temperature range that water is a liquid. Is that a coincidence? So the fifth and last reason why carbon is the only atom that can be used as the basis for life is that the energy levels of the covalent bonds that carbon forms with the other nonmetals that we need to make the molecules for life, well, those energy levels of those bonds are all very similar, which means that carbon molecules can easily take off a carbon, put on an oxygen, take off an oxygen, put on a nitrogen, take off the nitrogen, put the carbon back on. All of that is easily done because those bond energies are all very similar. Silicon has bond energies that are too far apart. So silicon can't take off a silicon, put on an oxygen, then take that oxygen off, put the silicon back on. Right? It just doesn't happen because those bond energies are too different. So carbon is absolutely necessary for life because carbon forms stable bonds with itself. Carbon can form up to 4 bonds. Carbon not only forms multiple bonds with itself, but also with other atoms. The energy levels of carbon-carbon bonds are just right for biochemical manipulation, and the energy levels of carbon bonded to other non-metals, those bond energies are all very similar. So carbon is absolutely essential for life. But where did it come from? Well, a few minutes after the beginning of the universe, the only elements that were present were hydrogen and helium and tiny amounts of lithium and beryllium. It took a few 100 million years for stars to form that could then make the heavier elements. Most stars fuse hydrogen into helium, and once a star has made helium, it should be easy in larger stars to add successive heliums to get beryllium and then carbon. Stars can build up the larger elements this way by fusing smaller ones. So for example, hydrogen and hydrogen can fuse to make a helium. Helium and hydrogen can fuse to make lithium. Helium and a helium can make beryllium. Beryllium and helium can make carbon. Two berylliums can make oxygen. So we can build up the larger elements in this manner. There are two problems with the formation of carbon in stars, though. The first problem is that three heliums could combine to form a carbon. But this is highly unlikely for three heliums to all collide in the same place at the same time. So the formation of carbon probably comes from a beryllium colliding with a helium. The problem with that is when beryllium and helium collide with enough energy to merge, there's too much energy for a carbon to form. Beryllium and helium both have positive protons in their nucleus, and for those to get together and to overcome the repulsion, they have to collide at extremely high velocities. They have to collide with enough energy so that the strong nuclear force can take over. That only happens if they get really close. So if this colliding beryllium and helium could collide with exactly the same energy as carbon, then the carbon nucleus could form. But this isn't what happens. The beryllium and the helium would have to have too much energy, so this collision looks as if it would just fall apart and not form carbon. So we're stuck. Three heliums is too unlikely, and helium plus beryllium has too much energy. So how do we get carbon? Well, it has to do with a property called resonance. Well, you probably learned about resonance in high school chemistry, where you learn that electrons in an atom could absorb energy and move to a higher energy level. Well, that's a different resonance. The atom can still exist, the atom is still stable, but its electrons are at a higher energy level. Those electrons can then fall back down to get the atom to a lower energy state, and it releases energy in the process. So those electrons being at different energy levels are different resonance states for the electrons. Well, nuclei can do that too. The nucleus of an atom can have different amounts of energy and be at different resonance states and transition between those and still be stable. So keep that in mind, and keep in mind that until the 1950s, the formation of carbon was a mystery. In 1953, though, Frederick Hoyle reasoned that the only way carbon could form was if there was a resonance state of carbon equal to beryllium plus helium plus that extra energy from the collision. This would mean that carbon could form at this higher energy state and then just release the extra energy to get to the ground state of carbon without falling apart. Well, this convenient resonance would dramatically increase the production of carbon in stars. And so here's what we think happens. Two helium collide to form a very short-lived beryllium, and then when this collides with another helium, a carbon atom is produced, but it's produced with energy equal to one of the stable resonances, or one of the stable resonance states of carbon. This carbon then releases extra energy in the form of gamma radiation to become a ground state carbon nucleus. So there just so happens to be a resonance level of carbon equal to that of beryllium and helium and extra energy. Is that a coincidence? Well, these resonance levels of carbon depend on three things. They depend on, one, the strong nuclear force. Well, that's the force that holds the protons and neutrons together in the nucleus. Secondly, they depend on the electromagnetic force. Well, that's the force that exists between charged particles, between plus and plus and minus and minus. And thirdly, the resonance levels depend on the mass that the quarks have. Well, quarks are particles that make up the protons and the neutrons. A proton is made of 3 quarks, 2 ups and a down, and a neutron is made of 3 quarks, 2 downs and an up. So all 3 of these properties all influence the resonance states of carbon. But all 3 of these properties is a very limited range of values that would still allow carbon to form. The strong nuclear force has a range of 0.4%, which means that if it were any bigger, if it were more than 0.4% higher, carbon couldn't form. If it were more than 0.4% lower, carbon couldn't form. The electromagnetic force has a range of 4%. Any higher, any lower, carbon wouldn't form. The mass of the quarks, however, have a very, very tiny range that they can take on compared to all the possible masses that a quark could have. They have a very tiny mass that they could take on. They can only vary by 1 part in 10 to the 23rd relative to all the possible masses a quark could have. So that's a really small number. And so to imagine it, imagine a fraction with a 1 on top divided by a 1 with 23 zeros after it. In terms of a percentage, that's a decimal point and then 20 zeros and then a 1. So that is a 1 21 places to the right of the decimal point in terms of a percent. So if the mass of a quark were any larger than that tiny fraction or any smaller than that tiny fraction, there would be no carbon. So to imagine how small this is, you have a 1 out of 10 to the 23rd chance of being struck by lightning 2.6 billion times each second, every second, over a lifetime of 80 years. So the conditions necessary for just the presence of carbon in our universe are exquisitely fine-tuned. Remember also that the properties that carbon has are also fine-tuned for human life to exist. In fact, it looks as if carbon was designed specifically to be the basis for life. Well, why is this important? Well, it looks like humans and the universe are not an accident. A reasonable conclusion from the science of carbon is that the universe was designed specifically for us to exist. And if that's the case, then someone had to design it. The only thing we know that can design is a mind that is capable of making free will decisions, or a person. This would mean that the most fundamental fact of the universe is a person. Personhood came first. Now, Christians believe that this person is God and that the universe was made by God for God's own reasons. This gives us intrinsic and objective value. This gives us meaning and purpose that are grounded in God's reasons for creating us. We have value, we have meaning, we have purpose that is totally independent of what we do or what we don't do or what we accomplish. Well, God's reasons for creating the universe and creating us culminated in the person of Jesus. Jesus came to earth to mend our fractured relationship between us and God. Because we constantly break God's laws, we are separated from God. So God himself provided a way to repair this relationship through the person of Jesus. God, the creator of the universe, wants a relationship with you, and you can have that relationship through the person of Jesus. The exquisite fine-tuning of the formation of carbon and the amazing properties of carbon that look as if they're both designed for life, for us to exist, they can point us to the person of God. God cares about us. He cares about you. He cares about you so much that he wants to have a relationship with you, and you can have that relationship through the person of Jesus.